Hello, hello, hello. Welcome back to Calc 2. This is now 7.4, and in particular, this time we'll worry about the arc length and the surface area formulas. So the arc length is going to be probably the most important formula from this section. The rotation formulas that you saw in 7.2 and 7.3, it turns out that we won't really use those all that much. We'll figure out new techniques in Calc 3 for handling the volume formula problem. The arc length formula, though, will come up again. Okay, so that one's not going to go away, and it turns out to be really important. And to develop the formula for arc length, we rely on the distance formula. Which you probably remember in the plane. The distance between 2 points is x2 minus x1 squared plus y2 minus y1 squared. And also then the mean value theorem, believe it or not, rears its ugly head. And so how did that go? Basically, if you have a continuous function that's differentiable on some interval from a to b, and you consider the secant line through these 2 points given this function f of x, there will exist some c value such that the slope of the tangent line at that point is equal to the slope of the secant line. In math speak, that will be f prime of c is equal to f of b minus f of a all over b minus a. All right, but the kind of connection between the distance formula and this formula is that you can think of f of b minus f of a as kind of a y2 minus y1, and then b minus a is kind of an x2 minus x1. So this critter right here, whenever you see it in the context that we'll be working in, you can kind of just replace it with this f prime of c. All right, so there's going to be this distance formula, and we'll be able to massage it algebraically and then do a replacement with this f prime of c, and then we'll get our hands on the arc length formula. And I think we could do this in context with problem number 1 in the book here. So they, not in the book, but in WebAssign. So they want us to figure out the distance between these 2 points, first using the distance formula and then using the arc length formula that we're going to kind of derive. Okay, so the 2 points, 2, 1, and then 5, 9. Okay, so using the distance formula, it's the square root of x2. So, you know, this is x1, y1, this is x2, y2. So x2 minus x1 squared plus y2 minus y1 squared. So what is that? It's going to be square root of 3 squared plus 8 squared, which is going to be 9 plus 64, which is going to be square root of 73. Okay, great. The distance formula, then the arc length formula that we are going to get. So this is like part A, I guess. Part B, it's this formula. We need to kind of get our hands on the formula. We don't even have it. It's an integral formula, and we could work with the Riemann person again. And this time, the Riemann person is going to be collecting kind of line segment distances. Okay, so we want the length of that curve there. We're not really, this time interested in an area underneath it. We just want to kind of take a ruler and measure the curviness, the distance on the curve there. So imagine a little person, or maybe the Riemann person, walking along the curve. How long is that? Okay. So to handle it, what we're going to do is kind of chop it up into a bunch of little pieces and measure the little pieces. Kind of like you can imagine you're taking a little ruler and you're measuring each one of these distances in particular, and then just adding up all the distances. Right? So you can kind of get an approximation to the length of that curve. It won't be perfect because obviously the curve is curvy and the little line segments we're adding up are not curvy. But let's see what one individual little line segment would be if we were to kind of get the distance of this line segment here, okay, at position x sub I. So we'll say that line segment has length change in x. And then the length of this little line segment we'll call s sub I. And we can use a distance formula to figure that out, right? So if you wish, you can kind of label these points, but at the end of the day, there's going to be some kind of change in x and then a change in y happening. So it'll be a change in x squared plus a change in y squared, and but that's pretty much it. In order to put it into something that's summable in the Riemann integral. We can factor this guy a little bit. So you want to factor out the change in x squared, and you'll end up with 1 plus change in y all over the change in x squared. Factor out the change in x thing here. And then you can factor out the change in x squared out of the square root altogether. And you end up with 1 plus change in y all over change in x squared. And then the square root of a change in x squared is just change in x, and then that thing you can have the Riemann person add that thing up, right? I mean, there's a lot of extra little details. We have to be a little bit more careful to get our hands on this formula. I mean, what the heck is change in x? What is change in y? You kind of have to label A as x sub 0, B will be x sub n. And then the x values around this x sub I, you could say maybe this is x sub I minus 1, and then this is x sub I. And then in the formula, the s sub I is actually going to be equal to the square root of x sub I minus x sub I minus 1 squared, and then plus f of x sub I minus f of x sub I minus 1, all of that squared. But what we're going to say is just, hey, let's just replace this thing with a change in x, and we'll just call this thing change in y. All right, so that's kind of how you can get your hands on this formula, and then you're sending the Riemann person across the x-axis to add them all up, right? So the overall arc length can be approximated by the sum of all these s sub I things. And then, of course, to get the actual value of the arc length, you're going to take the limit as the widths of those s sub I, of these change in x's, goes to 0. So anyways, this is going to be the limit of the sum of this thing, this 1 plus change in y all over change in x squared, delta x, and then the mean value theorem again. That's you could replace this, and you could think of y2 minus y1 as change in y all over change in x, and just replace that with f prime of c. Okay, so you could sit down here and then rewrite this thing. That'll be the limit of the sum of the square root of 1 plus f prime of c squared delta x, and then taking the limit, you end up the integral from a to b of the square root of 1 plus f prime of x squared dx. Okay, long story short, that's our arc length formula, and to kind of remember it, there's this distance formula flavor to it. It's just you're missing that initial, change in x squared part, but it definitely has kind of the archaeological remains of the distance formula in the ultimate form. But okay, so let's apply this to this particular problem given in the book. So part B, we want to find the length from 2, 1 to 5, 9. In order to pull this off, we're going to need a function of some sort for our integral. So to get our hands on the function, how are we going to do that? Well, you have 2 points. You can make the equation on the line from that, right? So the slope here, 9 minus 1 is 8, all over 5 minus 2 is 3. So our formula, the point slope formula, y minus, whichever y value you want, equals m, which is 8/3 times x minus 2. And then we got y minus 1 is 8/3 x minus 16/3. And then you can move the 1 over, so you get y equals 8/3 x minus 16/3 plus 3/3 is 13/3. It'll turn out that intercept really doesn't matter. What's important, because we're looking for the derivative of f, is just the slope, right? So in this case, y prime is going to be 8/3. And so our arc length formula, we're integrating from x equals 2 to x equals 5. So I'm going to put on the limits of the integral 2 and then 5. And then it's going to be the square root of 1 plus y prime squared. So you get 8/3 squared dx. Okay, and then our answer should be square root 73. So let's see if that works. The integral of the square root of the second guy is 64/9, and rewriting the number 1 as 9/9 to we are finding a common denominator and add them together. So we get the square root of 73/9 dx. And of course, you can factor that out of the integral, so that would be square root of 73 over 3. Remember, this is just the square root of 73 all over the square root of 9, and the square root of 9 is 3. And then integral dx. So from there, we have square root 73 all over 3 times x, and we're evaluating from 2 to the 5. So this will be square root of 73 all over 3 times 5 minus 2. So it would be square root of 73 all over 3 times 3. The 3's cancel, and you get square root of 73. So when all is said and done, you get the same answer whichever way you slice it. Of course, in our particular problem, we are introducing this new formula for arc length, and we'll be able to use this for any curve we come across, so long as the curve is relatively well behaved. It doesn't have a bunch of gaps in it. Doesn't have issues of differentiability. We'll be able to use this formula. Okay. All right. So after you get the formula down, and you will need that formula memorized for the test, but after you get it down, most of the problems just come down to kind of weird integration issues that you may have. So let's kind of get our hands dirty, and maybe just look at a couple of the variations on this theme that they'll throw in your lap. Let's try number 4. So number 4 wants you to find the arc length of the curve x to the 5th over 10 plus 1 all over 6x cubed going from 1 to 3. Okay, you don't need to plot or sketch these graphs at all, unless you want to. You can go on the Desmos and take a look at what it is. But in order to pull this one off, I need a derivative, right? You're going to need a derivative, and you're going to need to square it. To get the derivative, I'm going to rewrite it so it's a little easier to deal with. X to the -3 there. And okay, so now I can get the derivative. It's just power rule. So bring down the 5, you get 5/10, same as 1/2, x to the 4th. And then bring down the -3, so that's going to give me a -1/2, x to the subtracting 1, so you get -4. When we put it into our integral formula, so the arc length formula, square root 1 plus f prime of x squared dx, we need this derivative squared. We might as well go ahead and do that. Let's factor it a little bit to make that a little easier as well. Okay, so that thing squared, then you got to do a bit of foiling, right? So anyways, first off, I can just square the 1/2. So if you have a product squared, that's just equal to the individual factors squared. Right? This is one of your rules of exponents. So this will be 1/2 squared is 1/4 times x to the 4th minus x to the negative 4th squared. Right? And then I'm going to have to FOIL, right? So this will be 1/4 times x to the 4th minus x to the negative 4th times x to the 4th minus x to the negative 4th. Sorry, 1 second. I need to write something down. Okay, just 1 second. Foiling this thing, so it's 1/4. X to the 4th, you're adding exponents, right? So you get x to the 8th. Then the outer and inner. If you have x to the 4th times x to the negative 4th, you're adding exponents. So you get x to the 0, which will just be 1. So the outer and inner terms will both be -1. So you get -1 is -2. And then negative plus x to the -4 plus -4 is -8. Okay. And yeah, that's that second term. So we can dump it now into our integral. So the integral for the arc length from 1 to 3 is going to be the square root of 1 plus 1/4 times x to the 8th minus 2 plus x to the negative 8th dx. And then we want to clean up this integrand. So our ultimate goal usually is just to get rid of that stupid square root, because the square root function as it sits is not going to be integrable. So what I'm going to do is factor out the 1/4 from, believe it or not, this term and this term. So what will that look like? We'll have the integral of the square root of 1/4 times 4 plus the second term, x to the 8th minus 2 plus x to the negative 8th. And if you don't see that, just redistribute, right? Just multiply 1/4 times 4, you'll get back to 1. And then 1/4 times the x to the 8th minus 2x plus x to the negative 8th will give you 1/4 times x to the 8th minus 2 plus x to the negative 8th. Then the square root of a product is equal to the product of the square roots. So you can basically pull that 1/4 out of the square root. The square root of 1/4 is 1/2, and I'm going to pull the 1/2 out of the integral. Okay, and we can rewrite this with a half exponent if you wish. And then simplify a bit. So the only thing you can really do is add the 4 and the -2. So you get x to the 8th. And I'm going to write it in a very kind of, sort of, okay, so x to the 8th plus 2 plus x to the negative 8th, and then we got that raised to the 1/2 dx. Okay, so it may seem like all is lost, but this thing right here is something you could factor, okay? So this will be something squared, a binomial squared, and then when you take its square root, it'll go, you get rid of the square root. So, what times what gives you that trinomial? It'll be x to the 4th plus x to the negative 4th. If you FOIL that back out, you could see, all right, I get the x to the 8th plus 2 plus x to the negative 8th, and now the 1/2 and the 2 exponents will cancel, and you have something you can just integrate using a power rule. Okay. So I'll have 1/2, then x to the 5th over 5. X to the -4 plus 1 is -3 over -3, but I pulled out the negative into the front there. And of course now we're integrating from 1 to 3. So this will be 1/2. Let me rewrite it without the negative exponent, if you don't mind. And I'll be going to my calculator to tabulate to evaluate the answer. So I get 3 to the 5th over 5 minus 1 all over 3 times 3 to the third, which is 3 to the fourth, minus 1/5 minus 1/3. Okay. And the answer they want is 3 decimals. Be careful with your calculator. If your calculator is outputting answers that have 4 decimals, sometimes it'll round that 4th decimal place up to a 5, and then the 3rd decimal place, when your answer, you'll round up 1 more place on the 3rd decimal place, which will be incorrect when you put it into the computer. So make sure that your calculator has enough decimal places so those little weird approximation problems don't happen. Okay. So I'm just going to type this into my calculator and see what I get. And in my mode, when you're trying to make sure you have enough decimal places, I have something that says like display digits, and mine set it at float 10, so that usually gives you a bunch of a real big decimal. So if they want those 3 decimals, you're not going to have these issues that I was talking about. There's a lot of books that talk about these little rounding errors and things like that, which is really interesting if you're going into engineering, just to see like the mistakes. So the one that I remember is the time zone issue. The military, they didn't have their planes set up for time zones, so when they flew over the time zone, all the clocks, the inner clocks in the computers flipped out. It's like you're going back in time or something, I don't know, when you fly over time zones. And it's just weird things happen. And if you're an engineer, especially computer science, you want to be very, very sensitive to those kind of issues. Anyways, let's look at another one here. So a lot of these just come down to kind of like clever tricks that you have to have kind of embedded in your brain to pull off the integral. And so the clever trick here was kind of rewriting it as a square of a binomial, so you could take the square root and get rid of the square root. Number 5 is, what you'll see here, is a little bit more complicated of a problem. So we have y equals 3/2 x to the 2/3 plus 8, and we want to integrate from 8 to 27. So again, let's go ahead and get the derivative and square it first off. So I got 3/2 power rule, bring down the 2/3, and you get x to the 2/3 minus 3/3 is minus 1/3. Derivative of a is 0. So it should just be x to the negative 1/3. And then, of course, squaring that thing, you just multiply the exponent. So you get x to the negative 2/3. Then we're going to want to dump it into our integral. So we're looking for the arc length here from 8 to 27 of the square root of 1 plus x to the negative 2/3 dx. And look at this guy. So if you try to do a u sub right now, you're going to be in a world of hurt, because it's just not, you're not going to get the nice cancellation for the x terms, and the x's won't cancel. So the way you have to do it is a bit more complicated, and you kind of have to remember the process. So how am I going to do it, Mr. Stroop? Well, let's take a look. I'm going to first rewrite the internal part of the square root as a fraction. Okay, because then I can take the square root of the top and the bottom and kind of hope for a u sub cancellation there. All right, so I have 1 plus 1 all over x to the positive 2/3 inside the radical here. I'm going to rewrite that first term as 1 over 1 and get a common denominator. So I'm going to multiply top and bottom here by x to the 2/3. Okay, and then I'm going to end up with my expression, hopefully. So I'll have the integral of the square root of x to the 2/3 plus 1 all over the common denominator of x to the 2/3. Okay, so here I can then split up the square root. So the square root of a quotient is equal to the quotient of the square roots. Okay, so here I got the integral of the square root of x to the 2/3 plus 1 all over the square root of x to the 2/3. And then you could simplify that square root of x to the 2/3. Okay. So x to the 2/3, the square root of that is just the same as raising it to the 1/2 power. And whenever you have that parentheses case like this with exponents, you multiply the exponents. So x to the 2/3 times 1/2 is actually just x to the 1/3. So we can rewrite our integral as square root of x to the 2/3 plus 1 all over x to the 1/3. Okay. Okay, great. So I'm going to rewrite it again by changing the sign of this exponent to x to the negative 1/3. Then I got x to the 2/3 plus 1 dx. And believe it or not, that's going to be your u sub. Okay. That's going to be the kind of the thing that cancels the u sub. The u sub is going to be the stuff in the root. That's kind of our general rule anyway. So u is x to the 2/3 plus 1. And then du is going to be 2/3 x to the negative 1/3. There you see it, right? That's basically the derivative is sitting in front of the radical times dx. And then dx will equal 3/2 x to the 1/3 du. Okay, great. So got the integral of x to the negative 1/3 times the square root of u times dx, which is 3/2 x to the 1/3 dx. You add the exponents and the x stuff goes away, and you just have, well, you can factor out 3/2, and then you get u to the 1/2 du. I just only wrote dx, and let's write du. All right, and then it's power rule, and you're home free. So this will be 3/2 u to the 3/2 times 2/3, and I have to back sub, and then I can evaluate. So this will be u to, let's back sub, sorry. So this will be x to the 2/3 plus 1 to the 3/2, and then I want to evaluate from, what did we say, 8 to 27. Okay. And plugging in the numbers into the antiderivative, so you get 8 to the 2/3. Let's evaluate what these are, right? That's the same as 8 to the 1/3 squared. So that will be 2 squared, which is 4. 27 to the 2/3 is 27 to the 1/3 squared. So that'll be 3 squared, which is 9. Okay, great. So you should have then 27 to the 2/3 put in the top limit first. So that'll be 9 plus 1, which is 10 to the 3/2. I guess I don't need that first parentheses. And then minus 8 to the 2/3, we said was 4, plus 1 is 5 to the 3/2. And then we can evaluate that. Okay, so I got 10 to the 3/2 minus 5 to the 3/2, and I'm getting 20.442, okay, to 3 decimals. All right, let me give you a similar one for the quiz, the video quiz. So it's a similar problem, it just has different numbers. Okay, so y equals 3/2 x to the 2/3 plus 6, and then we want to evaluate from 8 to 125. Okay, so this is our video quiz. We want 3 decimal answer. Okay. Okay, so anyways, the next section in here is on surface area. And the approach is a lot like the rotation problems in 7.2 and 7.3. So I won't include the surface area problems on the test 1 turns out that we'll have other methods for surface area later on. Okay, so anyways, I want to develop the formula first, just like we have done previously with the Riemann person. So this time, Riemann person is running across collecting surface area values. Okay, so let's just take, for instance, this curve from A to B, call it f of x, and we're rotating this region about the x-axis, but we don't care about the volume, we just care about kind of the surface area of the results. So looking at maybe a little wedge of it here, located at some position x sub I, and we can kind of, we're not going to look at like a rectangle, it's more like a parallelogram thing, and all we care about is the outer portion of it, right? So when you do the rotation, what's going to be the object that kind of results? It's kind of like like this. It's like you took a strip of paper and kind of cut it and then taped it together somehow. And you're just looking for the surface area of that strip of paper, okay? And we have formulas for that. I believe it's the formulary for the surface area of a frustum of a cone. So, you know, here's a cone kind of shape, and then if you cut it like right here, that they would call that a frustum. So you have kind of a thing like this. And we know the surface area formula for this kind of item. The surface area for the frustum of a cone is 2 pi r times L. Okay, so the L value is this length right here, and we'll get that value using surface area formulas, the distance formula in particular. And then the radius is well, there's kind of like, you think of two radiuses, a radius on the top and radius on the bottom, but we average those radii together. And ultimately, because you're taking the limit as these objects get smaller and smaller, you could just think of it as one radius to describe it. Okay, so the radius value would be this distance ultimately. Okay, so for this object, the formula is for the surface area of this particular object is going to be 2 pi times the radius, okay, which is going to be this distance, this orange distance from the axis of rotation to the outer portion of the object, and that will just be given by the function f of x sub I, and then the L value, this distance, we can get using our formula for distance, which was that square root things, right? So we have the square root of 1 plus f prime of some point in that little interval there squared, and then times change in x. Okay, so this would be the r part from the 2 pi RL, and then this whole part right here is the L part. Okay, so the formula, sort of working formula, and again, you don't need to have this one memorized. This one is just kind of extra. 2 pi integral r of x, or depending on your orientation. I think all the ones in the homework were oriented with respect to the x-axis, and then from whatever A to B values. Okay, so let's take a look at the ones in the homework. I guess we could look at number 10 maybe, and then number 12 is a bit odd, so I don't know. Well, the mechanics of number 11 were kind of annoying, so let's look at number 11 and number 12. Okay, so first start with number 11, and write and evaluate the definite integral for the surface area, x-axis rotation. So y is square root of 25 minus x squared, and we want to go from -3 to 3. Okay, that y equals square root 25 minus x squared. That's the upper hemisphere of a circle with radius 5. It's negative 5 to 5. And they want us to send the Riemann-Man from negative 3 to 3, rotating about the x-axis. So the region we're actually rotating is from negative 3 to 3. And great. Okay, so it doesn't hurt to kind of identify the fundamental objects that we're working with. So in this case, the sort of rectangle that's generating these little reams of paper, or whatever you want to think of them as, is right there, of course. So we have these little strips of paper, kind of, don't know what else to call them. The radius value is from here to the top, right? So our R of x formula is going to be that square root 25 minus x squared. And then we need an L of x formula. So that will be a little bit more complicated, right? So again, the L of x formula is going to be the square root of 1 plus the derivative of y squared times delta x, or you can just put dx if you wish. So we need to get the derivative of y. So that will be rewriting that with a fraction exponent. Power rule it, 1/2 25 minus x squared to the 1/2 minus 1 is negative 1/2, and then the derivative of the guts will be negative 2x. And let's rewrite that and then square it. So this will be negative x all over 25 minus x squared, square root of. Okay, so squaring that thing, I'll end up with x squared all over, then the square root will go away, right? So it'll be that object. So the big L of x formula is going to be x squared all over, whoa, I got to put it in the square root thing, so it's even more complicated. It's going to be the square root of 1 plus y prime squared, which we just figured out was x squared all over 25 minus x squared, and then delta x, or dx if you wish. Okay, so yeah, the sort of setup is a lot more complicated in this problem. That's kind of why I wanted to do it. But anyways, the surface area is going to be the integral from negative 3 to 3 of, well, we need a 2 pi, and then we need the R formula, just square root 25 minus x squared, and then we need the L formula, which will be 1 plus x squared all over 25 minus x squared, and then delta x, or dx. Okay, it looks nasty, but it's going to simplify pretty well once you work a little bit with that second square root. So this will be 2 pi integral square root 25 minus x squared. Again, the square, you want to find a common denominator inside this square root here. So you can think of that first 1 as 1 over 1 right here, and then multiply top and bottom by this 25 minus x squared. And then you're going 25 minus x squared in the first numerator plus x squared all over the common denominator. And you can kind of already see there's going to be a nice cancellation going on. So we get 2 pi integral square root 25 minus x squared. The second square root is a square root of a quotient, so you can split that into the quotient of the square roots. 25 minus x squared plus x squared is just 25. Then the denominator, square root 25 minus x squared. See what I mean? A really pretty cancellation. And then the square root of 25 is just 5. I can factor that out, so I get 10 pi integral of just dx. Believe it or not. So I get 10 pi x evaluated from, what are the bounds here? Negative 3 to 3. Okay, so I'm going to get 10x times 3 minus negative 3, which of course is just 6, So you get 60, and I lost my pi. Oh, that's 10 pi, not 10x. If I could get the eraser to work, that would be great. There we go. Okay, so it's going to end up being 60 pi. Okay, so it looked pretty intimidating, but ultimately there's so many nice cancellations in the algebra that it's not too big of a deal. Number 12 is a bit of a nuisance. I think it's a snafu on the publishers, and because they just don't do all the homework like I do. But the deal is it really should have been put in terms of y. It's a y-axis rotation, so they should have sent the Riemann man up the flagpole. But they're trying to kind of be clever, I guess, and say, hey, you don't always have to do it that way. You could do it this other way. So anyways, let's see what's going on. So I have the cube root of x plus 2. They've given you the region that you're rotating via this picture. They don't really give you bounds or anything. So anyways, from the picture, it's, you know, the y coordinate is at 3. So that looks like it's going to be 2. Or no, it's 1. The cube root of 1, yeah, so it's at 1, 3. So if you plug 1 in, so y of 1 is equal to the cube root of 1 plus 2. So you kind of have to guess at what the Riemann person is running across, which values they're going from. So this cube root of 1 is 1 plus 2 is 3. So yeah, the output is 3. And then the other one looks like it's at 8, but you want to be sure, right? So you go y of 8 must be the cube root of 8 plus 2. Yeah, so that's 2 plus 2 is 4. So 1, 2, 3, 4, 5, 6, 7, 8 is up here at 4. And then they want to rotate this thingamajig about the y-axis. Okay, so anyways, we need 2 formulas, and they want you, they're forcing you to put both formulas in terms of x, okay, with the way they set it up. So we need an R of x formula, and then we need an L of x formula. And the things that are being rotated, you know, they're basically these, it's this thing right here, right? So in the picture you're going to have of your little strip of paper is going to be kind of like this. Okay, so the radius function, which needs to be in terms of x, looks like it's going to be the length from here to here, right? And for any particular given x position, that's just going to be x. So you could literally just keep the radius as x. And then the length formula is this distance right here. The L of x is the distance from this point to this point. So that's the square root function as usual. And we could use the y formula and get the derivative in order to get our L of x formula. So we just need this thing that goes in here and then square it, right? So the thing that goes in there is the derivative. So you know, I want to rewrite this as x to the 1/3 plus 2, and then power rule it. So I get 1/3 x to the 1/3 minus 3/3 and minus 2/3, and then that's what I put in here. And then the computation is going to be a little nasty. All right, so let's go ahead and dump it into our integral for arc length. This will be 2 pi integral. It looks like it's going from, what do we say, 1 to 8. And then I have the square root, well, there's an x for the radius, and then the length formula, square root 1 plus squaring, it will give me, and I'm going to rewrite it as a fraction. So it should be 1/9 x to the negative 4/3, but I'm going to rewrite it as 1 all over 9 x to the positive 4/3. Dx, and then we're going to find a common denominator, split up the square root, all that jazz. Okay, so we have 2 pi integral x. 1 is the same as 1, and then I want to multiply top and bottom by 9x to the 4/3. And we'll end up with, in the radical, 9x to the 4/3 plus 1 all over 9x to the 4/3. And then split up the radical into the quotient of radicals. So I have x here on the outside, and then square root of 9x to the 4/3 plus 1 all over 3x to the 2/3 dx. I could factor out a 3. I'll get 2 pi over 3 integral. And then x over x to the 2/3 is x to the 1/3. And then you can do a u sub for the stuff inside the radical. So let's do a u sub there. du is 9 times 4/3 x to the 4/3 minus 3/3 is 1/3 dx. And then dx will be, okay, so 3 goes into 9 3 times 1/12, 1 over 12 x to the 1/3 du. So our integral is now 2 pi over 3 times the integral of x to the 1/3 times square root of u, which is u to the 1/2, times dx, which is 1 all over 12 x to the 1/3. You see the x material is going to cancel. Okay, so I can factor out the 1/12. That's going to give me pi over 18. The x to the 1/3 are gone, and then I have the integral of u to the 1/2. It's supposed to be pi over 18. U to the 1/2 plus 2/2 is 3/2, and then times 2/3. And then I want to evaluate after I back sub. So it looks like it's going to be pi over 27. And 9x to the 4/3 plus 1 to the 3/2. And we said we're going from 1 to 8. Okay. So we pi over 27. 8 to the 4/3 is the same as 2 to the 4th, which is 16, plus 1 is 17. And then minus 1 to the 4/3 is just 1 times 9 is 9, plus 1 is 10. Oops, did I not multiply it? Yeah, it has to be 9 times 16 there. So this won't be 17. I forgot to multiply by the 9. So that would be 145 to the 3/2. Okay. And then we want to get a 2 decimal approximation. So go to your calculator and see how that works. So what do we got? 9 over 27 times 145 to the 3/2 minus 10 to the 3/2 is 199.48. Yeah, so I mean, the real part they're trying to teach you is just the setup, but then on top of that you have these kind of nasty integrals that take a bit of kind of have their own set of tricks associated with them, but more or less that's about the big and the small of it. Okay, so the main takeaway though from this section is that arc length formula that you see right there in the blue box, which you need for the test, and then kind of how to handle particular these two particular types of integrals, like number 4 and number 5. So I think if you can kind of master that for that portion of the test, you should be all right. Okay. So anyways, thank you for watching, and I'll see you next time.